So, we talked of varieties of nuclear reactions. In general, you write a nuclear reaction as a target nucleus X and then the projectile particle A, which is either a nucleon like proton or neutron, or a small nucleus deuteron, alpha particle, so on. And then outgoing particle B, which we detect in the detector, and the nucleus Y. So, this is the product, final product nucleus. Now, as we discussed, you have varieties of reactions. If this A and B is same, normally it is known as scattering, the same particle which comes out. Now, it could be the same particle which comes out, or maybe it is a similar kind of particle come out, that is also possible. The proton which you have sent on X, if that same proton comes out, then it is surely scattering, but if that proton gets absorbed and some other proton comes out, that will also be written like this, but that will be typical nuclear reactions. Now, scattering can also be elastic scattering or inelastic scattering. In elastic scattering, you have this particle coming in and then going out, and the total kinetic energy before the event and after the event are same, and that normally happens when you have low energy charged particle falling on the nucleus. Because of the Coulomb barrier, it is not able to penetrate close enough, and it is a Coulomb scattering, which is elastic scattering most of the time. Then inelastic constant scattering, you have this some energy goes into the system, excites it from ground state to some higher energy state, and final kinetic energy is less than what you would expect. Another thing which we will discuss is the change in the rest mass. From there you can get extra energy, or you may need energy to pump in to get that final products. We will talk that in somewhat more detail. The kind of reactions that we are discussing at this moment, and if A and B are different, X and Y are different, they are normally known as the reactions, typical reactions, nuclear reactions. Now, in this nuclear reaction, we talked of two varieties. One is what we call compound nucleus reaction, and other we talked of direct reactions. In this compound nucleus reaction, the it is a two-step process. So, this A falling on X gets absorbed into it for some time, and that creates a nucleus with some higher energy, and then after this nucleus decays in Y plus B. Okay. So, in this compound nucleus thing reaction, where, and this will be more probable when the energies are such that the de Broglie wavelength of the incident particle is more like the size of the nucleus. So, that the energy is shared by all the nucleons in the nucleus. It takes time, the energy is first goes into few nucleons or one nucleon, and then there are collisions among the nucleons, and from there the what you call equilibration, right. So, the energy is distributed finally in all this nucleus, and this compound nucleus is formed. And but this is in a higher energy state, and so it can emit the particle and or de-excite, go to its stable state. So, that is this second part. Whereas direct reaction is when the energy is still higher, say 20 MeV and above, so that the de Broglie wavelength is of the order of nucleon size, not nucleus size. In that case, it hits, interacts with one or two surface nucleons, and some nuclear reaction takes place there itself locally, and then something comes out and something gets into the product nucleus. So, that is a direct reaction. There are a variety of direct reactions also, but coming back to this compound nucleus reaction, the basic one of the basic assumptions in understanding this kind of mechanism is that once this C star is formed, once this projectile nuclei or nucleus A is absorbed into the target nucleus, and then the energy is equilibrated among all the nucleons, so that the compound nucleus is formed, then it has lost all the memory of how it was formed. Now, it is this state of this nucleus that decides the future course. Right. So, the detailed theory of compound nucleus is developed on this assumption. I will show you a slide in which we will have this proton falling on copper 63, and then this will make, so proton falling on this, it will make 64 zinc, and another way in which it can do is this alpha particle can go on 60 nickel, and that will also form 64 zinc. This is the compound nucleus, which will finally decay to something else. Okay. So, it can decay in various manners, it can be formed in various manners, and it can decay in various manners. So, after the 64 zinc is formed, that can decay too by emitting, let us say, neutron. If a neutron is emitted, it will be 63 zinc plus neutron, this is one channel. It can also go through 2 neutron emission. These are the observed things in the experiment, that is why I am writing this. I will show it on the screen. So, if 2 neutrons are emitted, then it is 62 zinc plus 2 N, or 1 neutron, 1 proton can also be emitted, in which case it will make copper and 62 copper. Many other things are possible, but the work that I am going to show you talks of these 3 mechanisms. So, if this zinc is formed, let us compare that this zinc 64 zinc is formed through this proton reaction. So, proton going into this, or it is formed in this alpha particle reaction, where alpha particle falls on 60 nickel and then it goes here. So, the later part, this zinc going into these channels in these reactions, this later part should be independent of how it was formed, provided the compound nucleus is formed in the same energy state. Okay. So, let me show you a slide in which these reactions are studied, and we will see that the assumption is has experimental support. So, look at your screen. This is a paper by S.N. Ghoshal, Physical Review 80, 1950, and on the screen you see the x axis, horizontal axis here. This is in energy. This is energy here of alpha particle in mega electron volts, and if you can see, this is 8 here, this is 8, and this is 16, this is 40. So, this is energy scale. On top of the figure, if you see here, also you can see here energy scale is written. This is also energy, but this is energy of proton in MeV. Okay. And here if you look at carefully, this is 5, this point is 5, and therefore, this point is 1. Okay, this is 1 MeV. So, here this it starts at 8 MeV in on the bottom line here. This is 8 MeV and it goes up to here it is 40 MeV. Here on the same graph you see energy scale on the x axis side, horizontal side, this is 1 MeV and this last point is 33 MeV. So, two different energy scales are used here, one for alpha particle, that lower horizontal line is energy of alpha particle in MeV, and the topmost horizontal line here is energy of protons in MeV, and the scales are shifted. So, for alpha the full scale in this diagram is 8 MeV up to this 40 MeV, the end point here, whereas in the case of proton it starts from 1 MeV and goes to 33 MeV. So, this is the same plot, is the same graph, but two horizontal scales are used, two different energy scales shifted. The scale is fine, the 1 centimeter is equal number of MeVs, but it is shifted, the values are shifted. Why values are shifted, that we will talk a little later. The values are shifted to match the energy available for excitation. How much? So, that 64 zinc should be formed in the same excited state if you want to compare the two incoming channel. Therefore, the energy will be shifted. So, we will talk about this when I go to the board. Now, look at the diagrams. So, look at this diagram here, these two curves here, right. Now, this upper one is written there, but I do not know whether you will be able to see small letters. This upper one is for reaction nickel 60 alpha, then Pn and copper 62. That means, this zinc 64 zinc is formed by alpha particle reaction on 60 nickel, and the lower one, this one, the lower one, this is for copper 63. Pn and then copper 62. So, what we are studying? We are studying how this zinc 64 decay to copper 62 emitting a proton, emitting a neutron. So, the final products are same, whereas the initial constituents forming this 64 zinc, they are different, and this graph shows how this cross section reaction probability changes with the energy. So, in both cases you see that the pattern is almost the same, the two variations, this one and this one, they are almost the same character they are showing. Similarly, if you look at the other part here on the left side, here you have this these two graphs, and here also the variation of cross section as a function of energy is almost the same. This one and this one, it is almost the same. And what are these two? This upper one is again alpha particle and falling on that nickel 60. So, the and then neutron coming out, zinc 63. Okay. And the lower one here is, this is copper 63 on which proton is falling, and then neutron is coming out and zinc 63 is formed. So, for the same final products we are comparing, with in alpha nickel reaction and proton copper reaction. So, the compound nucleus is formed in two different ways, but we are comparing the cross section for same final product, which is neutron and 63 zinc, neutron and 63 zinc. And here also you see that the two curves here, the cross section as a function of energy here and the cross section as a function of energy here, they are almost the same. Okay. Then you are left with two more curves here, erasing this. So, the two things left here are this region, these two. You can see there are two curves here almost overlapping on each other, this one here and this one here. Once again, these two correspond to two different reactions, but with the same final product. One is copper 63 and then proton and two neutrons coming out, zinc 62. This is one, and the second one is this nickel alpha. So, 60 nickel and then alpha and two neutrons coming out and zinc 62. So, for the same final products, whether it is formed due to proton reaction on 63 Cu or it is formed due to reaction of alpha particle on 60 nickel, the cross section as a function of energy is the same. So, that means the final decay is independent of how that compound nucleus is formed. So, that basic theory. So, keep this all this thing in mind. I am going to the board and I will tell you why these two energy scales are two different energy scales are used in this comparison, but the basic assumption of this theory, compound nucleus theory, that the incident particle gets absorbed into the nucleus, forming a compound nucleus in some excited state, and then because of that statistical collisions and sharing of energy by all the nucleons, that entire memory of how it was formed is now gone. Now, it is that compound nucleus in that particular excited state which has its own dynamics to emit that outgoing particle and make the product nucleus. So, that is the underlying theory. So, let me talk of that energy thing. If we want to compare, this say this reaction and this zinc 64 is formed through this reaction or through this reaction. So, if we want to quantitatively compare the cross section or the dependence of cross section on energy and so on. So, what you will need, you have to produce this 64 zinc in the same excited state, then only you can compare the two cases. So, what is that energy needed of the incident particle to take it to that particular excited state? So, that will be different for proton and alpha, and that is why the two different scales are used. So, let me talk in terms of the in center of mass frame, easy to do. So, in center of mass frame, suppose you have a proton here and this 63 copper here. Now, in the center of mass frame, the total momentum should be 0. So, if it is going in this direction, this will be going in this direction, and the magnitude of the momentum will be same. So, that the total momentum is 0. So, that is before the event, and once the proton gets absorbed into this copper nucleus making 64 zinc, then the whole particle should remain at rest in the center of mass frame, right, because the total momentum is 0. So, the total momentum must be 0, and since this is one single particle, so it has to be at rest. So, if I look at the energy considerations, what I have is, before the event, it is mass of proton and plus mass of this 63 copper times C square plus kinetic energy of the proton, which will be p square by 2 mp. So, the kinetic energy of the proton, this p is magnitude of the linear momentum of each of the two particles, because they have to be equal, and then the kinetic energy of this, which will be p square by 2 mass of Cu. I am writing the same p because in center of mass frame the magnitude of momentum here and magnitude of momentum here should be same. So, that is the initial kinetic energy before the event, and after the event the energy, total energy is mass of this zinc 64, let us take ground state, C square, and plus the energy which is taking it to some excited state, right. So, this delta E is equal to mass of P proton plus mass of copper and then minus mass of zinc, this into C square and plus this P square by 2 mp, which is kinetic energy of the proton, and plus P square by 2 mcu, which you can write kinetic energy of proton again and then mass of proton over mass of copper, right. You can write this as P square by 2 mp here and then mp by mcu. So, that mp by mcu is here and P square by 2 mp is kinetic energy of the proton. So, it is mp plus mcu and minus m zinc Okay. So, Kp you can write from here, and Kp will be delta E and minus Mp plus Mcu minus M zinc C square divided by 1 plus Mp Mcu. So, for a particular excitation energy delta E, you need this much of proton energy, and similarly if you work out the same thing for alpha plus 60 nickel and taking 64 zinc to the same excited state, how much alpha particle energy is needed. So, it is the identical analysis, only the proton and copper will be replaced by alpha and nickel, and therefore, you can straight away write the energy of alpha particle needed to take this zinc to the same excited state with the same excitation energy delta E, and that will be K alpha equal to. So, now it is K alpha. How much alpha particle energy is needed to take the 64 zinc to the same excited state. So, this delta E is same. So, this will be delta E minus mass of proton is now mass of alpha particle we will write. So, minus mass of alpha particle, and then plus wait. So, this is Kp is Mp. This is what, did I write it correctly? Let us check. So, this is Mp plus Mu minus this. So, this is equal to delta E and minus. So, wait. Let me do the correction. So, delta E and minus Mp plus Mu and minus zinc, right. It is like this. Right, it is like this. Now, it is dimensionally also constant. So, it is delta E and then minus, put a bracket here, and this is M alpha plus MCU. In place of that, it will be mass of that nickel 60, and then minus mass of zinc, that will remain there. So, minus mass of that zinc 64 times C square and then divided by 1 plus MP, here it will be M alpha, and divided by MCU, here it will be M nickel. So, now these two are different expressions, they are similar, but the numbers, when you go to put the numbers, mass of proton, mass of copper, mass of zinc of course. So, if you put the numbers here and if you put the numbers here, mass of alpha particle, mass of nickel, so these two things will come out to be different. So, alpha particle energy needed to put the 64 zinc into one excited state, and proton energy needed to put the 64 zinc in the same excited state. They are different. That is why in that plot you have seen that two different scales are used, one for alpha particle and one for proton, so that each point on that plot area corresponds to one particular excitation energy. So, that is how the compound nucleus reaction goes. Okay. Direct reactions can be different types. In direct reactions, this incident particle interacts with a small number of surface nucleons, and so it comes here and then makes the interaction here, and then something goes here. Now, one important variety is called transfer reaction. It's type of direct reactions. In transfer reaction, there is a transfer of a nucleon or more from the incident particle to the product to this target nucleus, or vice versa. For example, you can have what we call DP reaction, DPY. So, a deuteron falls on the nucleus X, deuteron is a neutron and a proton, and then it transfers neutron to this target X, making it Y, and the proton goes out. So, the deuteron is coming in and a proton goes out. So, neutron is absorbed here. So, it is transfer of neutron from this D to this P. Sometimes it is called stripping reaction. You can also have DN, this type also you can have, that is also stripping reaction. Reverse is also possible, a particle coming in and then picking up something from the target. So, PD reaction, this is also, so this is known as pickup reaction. So, here a neutron is transferred from the target nucleus to this incident particle. So, you have this PD reaction. Similarly, you can have many more transfer reactions, right. Then you can also have capture reactions, where a particle comes here and then it gets absorbed in this, say gamma particle is emitted. So, it is the same nucleus with n, of course, one nucleon number more. So, this is capture reaction. Okay. So, the particle, say in this reaction, this neutron comes here, gets absorbed, and then it goes to some excited state, and from there it can come down emitting some gamma ray. It can also emit something else. It can also emit a neutron by itself, or something else, that is also possible. But what we call capture reaction, if this gamma ray, it comes out, the outgoing particle is gamma ray. In that case, that neutron is permanently absorbed into that nucleus. So, there are varieties of these direct reactions. Okay. Now, the difference, visible difference between a direct reaction and a compound nucleus reaction. So, there are two differences mainly. One is time scale. Okay. For compound nucleus reaction, the time needed for that reaction to complete is much larger than what it will be for direct reaction. Why? This is because that energy has to be equilibrated among all the nucleons, and this takes time. The energy is deposited at some point in the nucleus, and then through collisions it is transferred to other nucleons, and through many more collisions it is distributed in the whole of the nucleus, and then a particle comes out. So, it takes time, but even that long time is very small as far as the laboratory is concerned. The time scale is something like, say, 10 to the power minus 15 minus 16 seconds. And the time for a direct reaction, that you can easily work out. In the direct reaction, the time available for reaction is almost the transit time for this particle to cross this nucleus. So, that can be estimated if you know the kinetic energy of this particle, and you know the distance, that is a nucleus size that it has to traverse. One can calculate this time. Let us do that. So, suppose the particle is proton, incident particle is proton, and let us say the energy is 20 MeV. For direct reactions, the energy has to be large. So, I am taking somewhat smaller energy here. So, I can calculate the speed of this 20 MeV proton. If this is the rest mass energy is 1000 MeV. So, let me do this non-relativistic calculation, and anyway we are doing order of magnitude calculations. So, half mv square, this is 20 MeV. From here I am trying to estimate this velocity. So, v will be equal to, this is 40 MeV and divided by mass of p, square root of that. So, multiply c square here and c here, and for rough calculations, mpc square, put 1000 MeV times c here. So, this is 4 by 100. So, 2 by 10, something like 0.2 c. 8 meter per second. So, if I take the nuclear size to be, let us say, 10 femtometers. So, if the nuclear size is 10 femtometers, the time taken by this particle to cross that nucleus will be 10 femtometers, and then divided by the 0.2 into 3 into 10 to the power 8 plus 15 is 23 femtometers and per second. So, this is going to be approximately, say, 10 power minus 22 or so. Okay. So, there is a huge difference in time scale. If this is 10 power minus 15 seconds, this is 10 power minus 22 seconds. So, that is one big difference, but it is still difficult to distinguish between these two. Modern equipments can do that, but it is still difficult for a typical experimental set. The other difference between these two, direct reactions and compound nucleus reaction, is the angular distribution of the outgoing particle. Means, if you put the detector at different angles, this is the target and your beam is coming like this, and then you put the detector here, so that you look the particles in this direction. How many particles are coming here in this direction? And you can put the detector at different theta. You can put the detector at different theta. Okay. So, this is the angular distribution, how the number of particles coming in the detector in a given time interval varies with theta. So, that angular distribution will be markedly different in the two cases. In compound nucleus reaction, if we talk in center of mass frame, where the compound nucleus is formed with 0 momentum, and then after this all equilibration, this compound nucleus decays, giving you some outgoing particle. So, there it is more likely that the distribution will be symmetric. Once this compound nucleus is formed and has lost all the memories of the previous direction of that particle coming in and hitting and all that. So, from here it is now emitting the particle and giving that product nucleus. So, here it is more likely to be symmetric in directions, whereas if you have a direct reaction, it just comes, nucleus is coming in the center of mass frame, the nucleus is coming this way, it is coming this way, and then some reaction is taking place. So, there that direction is important, and the distribution in different angles will be different, and more likely it is a forward peaked. So, you will have larger number of particles in that forward cone, forward directions, low theta, small thetas, and less particles. Of course, there are many more things, but nevertheless the angular distribution can be different, and from there one can really detect whether it is coming through a compound nucleus reaction or it is coming through a direct reactions. One more thing I would like to talk about, in fact two more things if time permits. One is energy considerations, right. So, if you have the reaction A plus X going to Y plus B, if I talk in lab frame, this is the particle A which is going in this direction, target is at rest. So, that X is at rest, this is lab frame, and then this particle A goes in some other direction, or some particle B goes in this direction theta, where I have put the detector. So, I am looking only those particles which are going in this direction, and this nucleus will recoil in some other direction here in at some angle phi. So, in this reaction, if you look at the energies, conservation of energies, initial energy, final energy, and all those things, then you can write 3 equations, because momentum also has to be conserved. So, in x direction, horizontal direction in this diagram, your equation will be P A equal to P B cos theta and plus P y, this is the y particle coming, this not coming out, this B particle is coming out, this y particle is still in the target. It will be stopped in the target. Normally the target is of some solid material. So, more collisions and thermal distributions, those things. As far as this nuclear event is concerned, it is recoiling in this direction. We do not observe this, it is still remains in that target itself, but it will be P y and then cos phi. Whereas, for the perpendicular direction, transverse direction, the initial momentum is 0, and therefore, that should be equal to P b sin theta and minus P y cos phi. This has to be taken into account. If I am looking for the energy conservations, these momenta are to be conserved, because they will also be contributing towards kinetic energy. Now, energy is initially you have mass of A plus mass of x times c square, that is the rest mass energy, and plus kinetic energy of A, and that should be equal to, finally you have mass of B and mass of y c square . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . and plus kinetic energy of the particle B and kinetic energy of this particle y, which we write P y square by 2 m y. Right. So, initial rest mass energy plus initial kinetic energy, the target nucleus is at rest in the target material, and then after the event this B particle is going out, is going into the detector. So, that mass, then this y product nucleus. So, this is the rest mass energy and the kinetic energy of particle B and kinetic energy of the recoiling product nucleus. I have written it in this form because this Kb we can measure in the detector, and Ka we have accelerated the particle A. So, that Ka is also known, but the product nucleus momentum, product nucleus kinetic energy, those things are not known. Phi is not known inside the target, that has gone into some direction. So, that we do not know. So, from here we should eliminate this P y and this cos phi, sin phi, right. Oh, wait, this is sin phi here. So, you have to eliminate that cos phi, sin phi, then eliminate phi as well as this P y, these are unknown quantities, then you will get the relation between the energies, kinetic energies and the rest mass energies. So, I can take this to the left hand side and write that as Q. So, Q is as usual m a plus m x c square and minus m b plus m y c square. So, Q value we had been talking for quite some time, the initial rest mass energy minus final rest mass energy, that we write as Q. So, if I take it to this side, then this minus this is Q plus Ka is equal to Kb and plus 1 over 2 my Py square. Now, Py square you can write from here, Py cos phi square plus Py sin phi square. So, from there you can write that Py square, and it is Pa minus Pb cos theta square. So, that is Py cos phi square and plus Py sin phi square, which is plus Pb sin theta square. So, that is Py square, and then 2 my I have already written. So, this is Kb plus 1 by 2 my, and here it is Pa square and plus Pb square and minus 2 Pa Pb cos theta. Kb 1 by, all right. So, here let us do some rearrangement. Pa square by 2 my, Pa square by 2 my, you can write this as Ka times Ma by my. So, this term I am writing Pa square by 2 my, Pa square by 2 ma is the kinetic energy Ka, and then ma by my is this. Similarly, this Pb square you can write Pb square divided by 2 my, this will be Kb, and then you will have mass of B divided by mass of this capital Y. So, this is this, and here it is minus, and let me write this 2 my so that I do not forget, and 2 minus 2 times P cos theta and Pa Pb, which you can write as 2 m Ka and 2 m Kb. Square root of 2 into mass into kinetic energy is the linear momentum. So, Pa Pb is square root of 2 m Ka 2m kb cos theta I have written, minus 2 I have written, 2my I have written. So, now recollect. So, let us write it as an equation in kb. So, let me first see the kb term is here and kb term is here. So, you have and kb term is here. So, you have kb and 1, this is kb and this kb I am writing and this kb I am writing. So, 1 plus mb divided by my, then square root of kb, square root of kb. So, with square root of kb, here is square root of kb. What you have, this 2 you can cancel and this 2 will come out. So, it is minus 2 cos theta. So, put minus here and then it is 2 cos theta, and which m is this? This is ma and this is mb. So, square root of ma mb ka, square root of ma mb and ka. So, I have written this 2 ma ka 2 mb, all these things I have written, and divided by my. Okay. And then what is left? So, we have written this, so plus ka times this. So, plus ka times mb by my, this is that this side, and minus q and minus ka, minus ka and minus q, this is equal to 0. I have not written excitation energy. This nucleus which is formed here, this Y nucleus, this may be formed in excited state. In that case, you have an extra delta E coming in on this right hand side. So, this final energy when you write here, there will be a plus delta E if it goes to the excited state. If you can add it here itself, or you can keep in mind. So, this is an equation. You can little bit simplify my plus mb. So, I am multiplying everywhere by this my, minus 2 times and then this cos theta square root of ma mb and ka. This my I have already multiplied, then plus or minus, write it as minus ka taken common from these two terms. So, minus ka taken common, it will be 1 minus mb by my, and I am multiplying by my. So, it will be my minus mb here, and then this minus q is equal to 0. Okay. Remember this q can be positive or negative, right. It is not alpha decay or beta decay that the final product must have smaller rest mass than the initial constituents. It is a reaction, we are sending particle with some kinetic energy. So, q can be positive or can be negative. So, now this is where is root kb? Here is root kb. This is a quadratic equation in root kb. This is root kb square here, and this is root kb here, and this is that constant term if I treat it as an equation in square root of kb. So, from here you can write what this root kb is and what should be the value of Ka for this reaction to go in. So, root kb, if you write, this will be minus b, that is cos theta square root of ma mb times Ka plus or minus square root of b square minus 4 ac. So, it will be cos square theta and ma mb and then Ka and minus 4 ac. So, plus, and this will be my and plus MB, and then it will be here Ka and then My and minus MB. Okay, you should check all those calculations. Ka, why is Ka MB by My? Ka, from where I am getting this term? I am getting this term from this one. So, it is Ma. With Ka it should be Ma. With Ka it should be Ma. Okay. So, all these things and then this whole thing divided by My plus Mb, right, plus Q. Check all the algebra. Okay. Now, you should put constraints that this quantity has to be real. So, and then this quantity has to be positive, this Kb has to be positive. So, put all those constraints and then you can work out that for a particular given reaction, and delta is 0 I have taken, you can put, if you wish to populate one particular excited state, that delta E will come there with that Q also. So, from here you can find what is the minimum value of Ka possible. So, if Q is positive, then the reaction can go anyway. So, there is no threshold energy, but if Q is negative, then demanding that Kb should come out to be real and positive from here, you have a threshold energy below which the reaction will not go, and that threshold energy will depend on this cos theta term, because that cos theta term is also there. Where is cos theta? Here it is cos theta. So, that cos theta term is also there. So, depending on which theta you have put the detector, there will be a threshold energy. After that the reaction will start. So, all these energy consideration, those kinetics are to be taken into account if you study this nuclear reaction. Just quick comment on something else, and maybe we will talk little bit more about that in the next class, and that is, if you have from here you can also get what is the energy needed to just excite this final product into the delta E state. So, if you have this final product here at this delta E state, and then you are sending the particle with certain kinetic energy, which allows a certain energy to be deposited here, keeping all that momentum conservation into consideration, then the reaction probability of this excitation, that depends on the matching of this energy available and this energy here. If the energy available is less than this, it will not be excited, fine, but if the energy available is more than this, it can be excited, but then the probability will depend on what is the difference in that. We will talk about that in the next lecture.